Hello everyone. In this video I'm going to be discussing units. So units are something that you have to include anytime that you take a measurement. And the reason why units are so important is because they basically clarify what the heck you are talking about. And so for example, if you call up your friend and you say, "Hey, I'm going to be over there in 5," and then you hang up, then you're leaving your friend to wonder 5 what? 5 minutes, 5 feet, 5 nanoseconds, 5 gallons for some reason. And so in this case, units are necessary in order to one, tell what scale you're talking about, and two, it also kind of gives you an idea of how big or how small that measurement is. So a kilogram is much larger than a microgram. And so if you don't include your units, basically you're leaving your whoever your reader or your person you're talking to in a whole world of wonder. And so the two types of units systems of units that you're probably more familiar with is the first one is the English system. And so, as much as I love the US, we are way behind in our English system. This one we still for some reason keep around, and it's only used in the US, and it makes no sense whenever you talk about it from a scientific stance. And so what I mean by that is if you talk about length, and so length, you have inches and you have feet and you have miles, you have all these other kind of concepts. And so there is no real kind of connection between 12 inches and 1 foot and 5280 feet and 1 mile and even volume. You have ounces, you have cups, you have everything that just kind of hurts your brain by looking at it. So, for example, and again, please note this is not to scale, but if you have 1 inch, there is no real sense of an inch. I mean, an inch is made up of 16 little pieces, and so you can't really say something about 3/10 of an inch because there is no such thing about it. And so in these measurements, going from an inch to a foot to a mile to even a yard, you have to kind of mess around with a bunch of calculations in order to kind of convert these values. Or even just looking at a measuring glass or measuring cup. And so in this case, even this one in particular, you have 1 cup, you have 8 ounces, you have half a pint. There's so many different values that you have to use. And so anytime that you're cooking, you have to have, again, a whole mess of different measuring devices because they're all going to be different measurements, different calculations to get from one to the other. And the last thing I need to talk about in terms of the English system is the temperature. So the temperature is measured in Fahrenheit. And so if you have any feelings for any of your instructors in the science field, never give them a temperature in Fahrenheit. It just hurts our brains. And I'll discuss why here in a little while. And on the other end of things, everywhere else in the whole entire world and in the science field, we use the metric system. And the reason why we use the metric system is because it's what they call a base 10 system. And so the base 10 system just means that everything is made up of a bunch of values that you can either take zeros away from or add zeros to, and you have a different type of measurement. And so if we look at a meter scale, you have 10 millimeters in 1 centimeter. You have 100 centimeter in 1 meter. And so you can very easily convert 50 millimeters is going to be 5 centimeters. And so all you need to do is take zeros away and add zeros in order to get from one form of that unit to another. And the same deal if you look at volumes. And so volumes, they use liters. You have milliliters, you have kiloliters, you have deciliters, but all the difference between those is just a combination of adding zeros or taking zeros away. And the last one here is temperature. So temperature is measured in Celsius in the metric system. And this one makes sense, again, in the scientific community because water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. And again, 100 can be very easily divided by tens or ones, and it makes a little bit of sense. Or on the English side, again, I'll touch on this here in a little while, but water freezes at 32 degrees Celsius and water boils at Fahrenheit, and water boils at 212 degrees Fahrenheit, which is just weird numbers to begin with. And so, don't be scared at this next slide. I just want to give you a heads up. I do not require you to memorize all of these conversions here. I'm just throwing them at you to show you that if you want to go from the metric system to the English system, there's some conversions that you need to be aware of. It's not going to be as simple as saying 1 meter is equal to 3 yards, because that's not really accurate. And so in these cases, you have to make sure that you have some type of conversion handy if you want to go from the English system to the metric system. But there is one on this slide that I expect you to memorize and fully memorize for all the exams. And I even try to pinpoint it out here, but here's an arrow for you. You need to memorize this one right here. So 1 inch equals 2.54 centimeters. This is the only measurement on this slide that they are going to be considered exact. And so this is not a measured value, this is an exact value. And so it's going to be a perfect equality, and the only conversion that you really need to memorize to convert from English to the metric system. Because everything in the English system can be broken down to inches. Everything in the metric system can be broken down into centimeters. And so if you can convert it from inches to centimeters one way or another, you'll be fine. And so, because there's two systems, this kind of brings up an issue if you're a person in America writing a journal and you're writing things out and you're like, I used 6 ounces of this and I mixed it with 13 cubic feet of this, because someone in China is not going to have any idea what the heck you're talking about. Because again, they don't use ounces because it doesn't make any sense. But again, the scientific community needs some common way to speak to each other. And so a person in America can write a journal or scientific journal, experiment, and someone in China, someone in Russia, someone who speaks English on Mars can read these things, and again, they can make sense of what the heck you're talking about. And so in order to kind of make everything a common language, scientists use what they refer to as SI units. And so SI stands for the International System of Units. And I understand international systems is IS, but it comes from a French word, and I'm not going to try to pronounce that. And so SI units are the standard measurements that all scientists use all around the globe. And so one thing I have to make perfectly clear on this slide, and I'll say it a few more times throughout this video, there are only 7 base SI units, or they call them fundamental units. There are only 7 of them. Everything else is going to be derived from those 7 base SI units, and they have the proper term of derived SI units. And so the SI term is going to be thrown around a lot. You have SI units of density and volume and mass, but there are only 7 base, one more time, base SI units. Everything else is going to be derived, and I'll explain what I mean by that here in a few minutes. And so these are the 7 base SI units. And so you have mass measured in kilogram, length is measured in meter, time is measured in seconds, temperature is measured in Kelvin, which is new, and I'll talk about that, and the amount of substance or the amount of stuff is going to be measured in moles. And so electrical current and luminous intensity, those are the other 2 base SI units, but I'm not going to touch on them. So know they exist, and know there's only 7 of them. 7, that's it, just 7. And so, whenever we talk about derived SI units, I mean the fact that some other units exist. A lot of other units exist besides those 7. But all of those other units are going to be using the base SI units to make, or I guess to come up with whatever units they're talking about. But again, they are not base SI units. They are referred to as derived, or they're just called SI units. And so one example is volume. And so volume's SI units is going to be cubic meter. But the way that volume is derived is, again, just using the very basic equation for volume is going to be length times length times length. If you're talking about a cube, it's length cubed because all 3 of those lengths are the same. But in each of those situations, going back to our base SI units, length is measured in meter. And so here, if you have length times length times length, the unit for each one of those values of length is going to be meters. And so basically you have volume equals meter times meter times meter, or the base SI units of length are going to be derived into a unit of cubic meters for the derived unit of volume. And so hopefully that makes a little bit more sense. But if not, here's another example. And so velocity, its SI units is going to be meters per second, because the equation for velocity is length divided by time. The base SI unit for length is going to be meters, and the base SI unit for time is going to be seconds. And so the derived SI unit for velocity is going to be meters per second. And so you even have another example, and this one here actually I call it like doubly derived, because in this case density has the equation of mass divided by volume. Mass has a base SI unit. The base SI unit for mass is going to be kilograms. But again, volume does not have a base SI unit. Volume is a derived unit, which we derived above, is going to have a SI unit of cubic meters. And so even though that volume is not a base SI unit, it's still going to have a SI unit derived from the base SI. And so here the SI unit for density is going to be kilograms per cubic meter. So hopefully that makes a little bit of sense, but if not, again, shoot me an email. I'll try to explain it a little bit more detail for you. And so the next concept we have to explore is temperature. And so as I mentioned, there are two different scales that you're familiar with in terms of temperature, Fahrenheit and Celsius, and I'm going to explain a little bit more detail what I mean by Kelvin. But first, I want to talk about what we actually mean by temperature. And so temperature in the scientific world is a measure of thermal energy. And so thermal energy, in layman's terms, it's just heat. And so when we talk about thermal energy, you have to understand that all that's really happening when you heat something up is you're just increasing their jiggleness. And so every single atom, even if it doesn't really appear to our eyeballs, at some very, very microscopic level is jiggling. And if you heat something up, you're just inputting some energy into those atoms, and they just jiggle faster. And the same concept, if you take your two hands and you rub your two hands together and rub them faster and faster, you feel heat. And it's the same thing as you are generating thermal energy by rubbing your hands to one another. And so when we talk about temperature, one thing you probably don't really think about is temperature is always going to be relative to two objects. And so whenever you walk out or walk inside from outside and you say, man, it's hot, you're usually saying it is hot outside compared to inside. Or if you touch something that just came out of the freezer and you're like, man, that is cold, you just mean that that object is colder than its surroundings. And so when we talk about these temperature, it's going to be, again, a relative measurement between two objects. If something is hot, hot compared to what is something that you never really think about. And so, talking about these scales in Fahrenheit. So Fahrenheit, as I mentioned earlier, it is a goofy measurement. Nobody in the science field likes it. And so water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. And so this is the measurement we still use in America, and especially the one that you're more familiar with is the weather system. But most of the time, again, if you were to call up your friend and say, hey, friend who lives in China, and tell them it's 100 degrees outside, they would have a heart attack. They would probably think that you are on the verge of spontaneously exploding. And so again, Celsius, on the other hand, makes a little bit more sense. Because Celsius, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. This is where, again, we use everywhere else in the world, and when we kind of talk about the sciences. And so the last one we have to talk about is Kelvin. So believe it or not, if you lived in Texas your entire life, you might not believe me, but you can have a negative degree Celsius. But the problem with that is if you plug in a negative value into these equations we're going to start bringing up in later chapters, you end up violating some laws of science. And so if you plug in a negative temperature into the ideal gas law, it results in either a negative pressure, which doesn't exist, or a negative volume, which literally means you are less than nothing. And so you can't have a negative temperature when you start plugging these things into equations. And so luckily, Lord Kelvin, back in his day, was kind of a thief. And so Kelvin saw that Celsius's temperature scale, it worked great, it was perfect, except for the fact it can go into the negative. And so all Kelvin really did is he just took Celsius's scale and he just moved it up. He just figured out the coldest degrees that Celsius can be, and he just made that the new zero. And so in this case, the coldest that you can get to in degrees Celsius is negative 273 degrees Celsius. And so all he did is he changed that 273 degrees or negative 273 degrees Celsius into a zero. And then from there, he just kind of changed everything and like all the way up his scale. And the other special thing about Kelvin, I'm not sure what kind of aversion he had to degree signs, but Kelvin just doesn't have a degree. And what I mean by that is, you notice Fahrenheit and Celsius, they both have this degree sign. Kelvin doesn't have a degree sign. I don't know why. You might have to do some research on that one. And so, I want to hopefully kind of make this a little bit more clear. Celsius, it makes sense. You have water freezing at 0 degrees Celsius, boiling at 100 degrees Celsius. The coldest it can ever be is negative 273.15 degrees Celsius. Or on the other hand, we have Fahrenheit. I will never ask you anything in Fahrenheit. I do not want any measurements in Fahrenheit. If you're in the lab, you may get in trouble if you put anything in Fahrenheit just because it's very horrible in the science field. And so there is some equations. I don't expect you to memorize these because I never have anything in Fahrenheit, so I don't even know that equation. But Kelvin I do want you to know about. And so you need to memorize the number 273.15. Or at bare minimum, you need to memorize 273. That is the conversion between Celsius and Kelvin. And so as I stated earlier, all Kelvin did is he looked at the Celsius scale and realized that negative 273.15 degrees Celsius is the coldest it can be. And so Kelvin had the same exact scale, he just changed this value to a 0. And then changed everything going up by the same amount. And so now the 0 Kelvin is going to be the coldest it can be. The 273.15 Kelvin is where water freezes, and 373.15 Kelvin is where water boils. So please notice the difference between these values. 0 plus 273 will get you to the Kelvin. 100 plus 273 will get you to the Kelvin. And so, in these cases, you need to be aware of Kelvin and Celsius because we are going to use them a whole lot throughout the semester. And so, the next slide is where some people kind of start having some frustration and issues. And so these prefixes are definitely going to be required. You need to know everything about these prefixes. You need to memorize them. You need to know the symbols, and you definitely need to understand how the multiplier works. And so the SI system, or even just the metric system itself, uses prefix multipliers. And what I mean by that is you can convert your centimeters to megameters to nanometers just by changing the nano, micro, and deca, but the number doesn't change. The zeros, the number of zeros, it changes. But again, it's just by the power of 10. And so in order to go from kilo to centi to pico, you just take off zeros off of your overall number. And so one thing I just throw in here, just because this is a science class, angstrom, this is just a value that we typically use in order to measure bond lengths. You don't need to memorize it, but it's in between 9 and 12, so I just thought I'd throw it in there. The other ones you need to memorize. And so, before you take a look at this slide and freak out completely, just bear with me, I will walk you through it here. And so, the way that I have my table set up is my prefixes and my multipliers, you just really need to replace them. And so if you are given something like 1 kilogram, look on this table here, and you see kilogram is equal to 10 to the 3. And so in this place, you use the same number, that 1 sitting in front of the kilogram, you'll carry that 1 over. All you need to do is replace the kilo with 10 to the 3 and keep the units the same. And so this 1 will carry over, and that kilo would be replaced with 10 to the 3. Because we're talking about kilograms, your grams are still going to be the same. And so in this case, 1 kilogram is going to be 1 times 10 to the 3 grams. Another example is if we have 5 milliliters and we want to convert that to liters. And so in this case, do the same thing. Find where milli is on this table, and you see that milli is equal to 10 to the negative 3. And so here, you'll still keep the 5. You just replace the milli with your 10 to the negative 3. You're dealing with liters, so keep your units in liters. And so 5 milliliters is 5 times 10 to the negative 3 liters. And one more, 100 picoseconds. And so same deal applies. pico on this table is going to be 10 to the negative 12. And so you keep the number 100 and you replace the pico with times 10 to the negative 12. You're dealing with seconds, so keep your seconds. And so in this case, it's a very, very quick, easy conversion between the different sizes of your units. Whereas if you were dealing with the English system, you'd have to go from inches to feet to yards to miles, and it just gets confusing after there. And so using the prefixes, all you need to do is change the prefix in front of your unit, and you change the size of that unit. There's no crazy conversions or anything else you have to do there. And so I know units can be really kind of messed up and scary, especially because you see them written all different ways throughout different chemistry books. And so one thing I want to make clear here is it doesn't really matter how it's written. As long as you have your equalities written correctly, then again, you can say if there's 1,000 grams in a kilogram, there's 1 kilogram in 1,000 grams, it doesn't really matter. And so in this case, I will talk about what I mean by small things and big things here. All I really mean is if you're talking about going from centimeters to kilometers, kilometers are much bigger than centimeters. So you need to have a whole lot of centimeters in a kilometer. But if you're talking about going for kilometers or centimeters, you need to have a very small fraction of that kilometer in 1 centimeter. And so going back here, all I really mean by these units is 10 to the 3 grams or 1,000 grams equals 1 kilogram is saying the exact same thing as writing out as 1 kilogram equals 1,000 grams. That kind of hopefully should make sense to you. But the other end here is if we say something like 1 gram is equal to 10 to the negative 3 kilograms, it is the same exact equality. We're still saying 1 gram, we're still saying kilograms. We're just telling you that there is a whole lot of tiny grams in 1 big kilogram. But there is going to be a very, very small fraction, like 10 to the negative 3, small fraction of a big kilogram in 1 gram. As long as you keep this straight, again, hopefully it shouldn't matter, but you just need to make sure that you write these equalities down correctly. So, what I mean by big things and small things. If you have a big, big elephant and a tiny, tiny mouse, and so in this case, you should kind of understand the concept. It should take a whole lot of those tiny mice to equal the mass of an elephant. But on the other end of that, it's going to take a very small fraction. And I say like the massive like the elephant's toenail, but I don't really hang out with too many elephants. But it's going to take a small fraction of that elephant to equal that mass of the mouse. And so all I mean is you have to have a lot of small things to equal one big thing. Or you need to have a fraction, a very, very small piece of that big thing to equal the small thing. Hopefully big things and small things make a little bit of sense here. And so one suggestion I have for you is do some practice. I have a few practices already on Blackboard as soon as things open up and get running. But also, if that's not enough, Google unit conversions, and you'll find way more practice than you ever want to know even existed.